it's my great pleasure to have Sufei from RPI come here talk about his very exciting work about the light matter interactions in novel 2D materials. And you can see beautiful pictures. And first, I want a short introduction about Sufei. I know Sufei from long ago, I think, when he was a postdoc in Berkeley. And he worked with a well-known one in our field, Feng Wang, who's Tony Hen's student and now is a professor in UC Berkeley. And Sufei did a postdoc with him. And before that, he was a student in Cornell University Department of Physics. And he also get a degree from there. And his bachelor degree from, also master degree. Oh, you have master degree from Brown University, I don't know it. And his bachelor degree is from Nanjing University. When I was a student, that's the best condensed matter program in China. And so welcome him with us and give us a very exciting advance in the field.
Okay, thanks everyone. Thanks for attending. Today I'm going to show you what we've been working for the last few years, and it's mostly focused on excitonic physics in 2D. Before we start, I want to give you a very brief introduction about this particular material what we are working on. We've been working on quite a few different materials, but for the continuity of the talk, I'll be only focused on this so-called transition metal dichalcogenide, which is well known as MS2, WS2, and so on and so forth. Why this material is interesting? There's twofold, at least two major reasons. One is this material is it's atomically thin. As a result, the exciton binding energy is extremely large. So for three-dimensional material, you have this dielectric screening where the electric field lines within this material. If the material is 2D, actually, can I take the mask off? It's actually a little bit annoying. When the material is 2D, the field line goes mostly into a vacuum, so the effective dielectric constant is small. As a result, Coulomb interaction is enhanced, so the so-called binding energy will be large. So now, when the light creates electron hole pair in the system, instead of just responding electron hole pairs, because of this enhanced Coulomb interaction, the binding energy between electron hole is very, very large. We call it excitons, and the energy of exciton is significantly smaller than the band gap. So the photon energy you see is going to be at a lower energy of the band gap. One of the exciting things of this material is that the binding energy can be on order of 100 millieV to 1 eV, much larger than thermal fluctuation. As a result, a lot of excitonic devices people dreamed before is possible even at room temperature operation. So that's one thing, strong exciton binding energy. And there's another thing special about this material, that's the Valley degree of freedom. So it's a quantum degree of freedom potentially can use for quantum computing, so on and so forth. Why have this new degree of freedom? So if you go to the Brilliant zone, you have this band structure. And if you zoom in to the corner of the Brilliant zone, you have this called K and K prime valley. You see band structure as such. There's a very large spin-optic coupling. So the valence band is split. You can see that although the energy is the same, but the valence band maximum is different in terms of spin for K and K prime. So these two give you a different selection rule. So this can be pumped or pumped through circular polarized light. So this Valley degree of freedom essentially can be controlled by the circular polarized light. If you write down Hamiltonian, this Valley degree of freedom is very much like a spin. That's why it's called Valley spin. As a result, a lot of quantum information carrier based on spin can be realized with a Valley degree of freedom. So these two things, this Valley contrast excitons, become a really exciting opportunity for this material. That's why we start to work on the journey of this material. So today I'm going to give you some brief overview of what we've been doing. For the time's sake, so how much time do we have? Roughly 40 minutes, 50 minutes?
50 minutes.
50 minutes. So for time's sake, I'm going to focus on the excitonic fine structure of WSE2 for the last few years by improving the material, by understanding the system better. We understand all the possible excitonic complex in this system. One of the motivation is looking for this long-lived, very contrast quasi-particle. That's the motivation. I'm going to very briefly go through what we can do with a very large magnetic field. Essentially, if you have Landau quantization, what this excitonic behavior will be, and there's some new opportunity there too. Instead of monolayer, we can stack two layers together by engineering the band structure. There's some exciting opportunity there. For time's sake, I'm going to very briefly just go through this a little bit. I do want to talk about all these correlated states in the Mauricio lattice we recently studied, essentially by stacking this two-layer material with precise angular control, you form the so-called Mauricio lattice. You can have flat band, you see a correlated electron state, and most excitingly, you see the interaction between correlated electrons and excitons. So first, let's discuss the fine structure of monolayer WSE2. Why monolayer WSE2? So I told you the spin-up coupling splitting in the valence band, but there's untold story is the conduction band also have the splitting. It's much smaller in energy, so the valence band splitting is typically on the order of 300 millieV to 500 millieV. It's huge. This one is roughly 20 to 40 millieV. But for WSE2 and same for WS2, there's a special property. If you look at the conduction band minimum, it's a spin down. What does that mean? Obviously, if you create an electron hole pair, that's minimum energy for electron. That's the minimum energy for hole, right? But if you look at spin configuration, this one is spin down. This electron spin up, hole spin is down. So electron hole pair, the total spin is going down, right? The net spin is non-zero. As a result, this transition here is optically forbidden. It cannot direct absorb light. It cannot direct emit light. So the ground state of this exciton in this material, WSE2, same for WS2, is actually so-called dark exciton. The exciton you see can only be coming from this pair. So the light you actually see from the exciton combination, the bright exciton is actually excited state. So back in 2015, Tony Hines was able to study the temperature dependence of the PL and actually speculate that that must be the case. We also, along others, also show direct evidence of this one. This actually has significant consequence because dark exciton has much longer lifetime. As a result, has a very large population, and that actually gives rise to a lot of exciting physics in this material. So what we do, well, over the last 4 years or 5 years, 4 years, so we've been trying to improve the quality of the device. Essentially, we can make a structure encapsulated with boron nitride. The most important thing is that the interface should be extremely clean. And you can use graphene as the electrode. Here you have graphene as a top gate to gate the material. This is early work. Now we can do much more complicated structure than this, and I will show you data later. This is typical optical image. So the device will be roughly 10 or 20 micron in size. Here is one of the, probably the take-home message is, this is the spectrum of the monolayer WSE2. This axis is energy. So that tells you that resonance at a different frequency, at different wavelengths. This axis is a gate voltage that controls the doping. So around 0, it's roughly intrinsic. Here it's N dope, the electron dope. Here it's P doped. So one thing I want to mention is that within this range, all this resonance you are seeing corresponding a physical quasi-particle associated with exciton, one way or another. And the first part is I want to show you our journey to identify them. Again, the motivation is to find a long-lived quasi-particle that has a valid degree freedom. So that's the goal. This one, if you don't have a clean sample, what you see is a big block here. You won't see all these fine structures. So this is exciton. That's well known. What's exciton? We said the bright exciton is one electron here and one hole here. This one here, X plus, that's corresponding to a P doping site. You add a free hole in the system. So once, because Pauli excretion principle, the hole can only be here. So it form a 3 particle we call p trion or positive trion. For these two, you just add an electron in the system. The electron can be either here or here. These two configuration has different energy, different by exchange interaction, roughly 7 milli eV. So that's p trion 1, n trion 1, n trion 2. So these are all known before us. So this not a claim, but these are all well known excitonic physics in the field at the time. But there's a lot of other features which was not known yet. Yes.
So how do you actually distinguish trions from excitons here? Presumably you need more than just this photoluminescence data.
Yeah, definitely. So this is exciton, that's well known, right? So trion meaning like one exciton bound to a free electron hole. So in principle, this additional Coulomb interaction will lower the energy. So emission of the photon will be at a lower energy. So this one is, so the energy in this case, it's slightly tricky, but the binding energy is given by the PL resonance of this one and this one. So you can see this emission is roughly 20 milli eV below the exciton. This one is 30 milli eV below the exciton. And this has been done by many, many calculations showing that's the case. So that's I mean, there's other signature we will see later. There's B field dependence, gate dependence, and so on and so forth. But that has been done before us. So people have reasonably good understanding of the system, but there's a lot of rich physics behind. One natural question to ask, well, like gallium arsenide, what's biexciton? Understanding biexciton is extremely important to understand nonlinear property, especially for lasing of these materials. So actually, as early in 2017, again, Tony Han's group was able to show the power dependence of PL, showing that one additional peak, which they call XX1, has a nonlinear power dependence, which is actually a superlinear power dependence for biexciton, because the combination rate is proportional to n squared. So you suppose the power law is going to be showing this is the power intensity, that will be alpha will be 2. But for practical reason, it's less than 2, but still larger than 1. So that's the signature of biexciton. The problem is that the energy of this one, as I said, the energy difference between this one and exciton give you the binding energy, right? It's roughly 50 milli eV. This is way too large. For calculation reasons or intuitive reasons, you will see this one is larger. One very simple argument is that if biexciton, right, the Coulomb interaction of exciton is dipole-dipole interaction. In principle, it should be less than dipole-monopole interaction, which is trion. So in principle, biexciton binding energy should expect to be less than trion, which is roughly 30 milli eV. But now we have 50 milli eV. This is counterintuitive. And there's also tons of calculations showing that it does not agree. So that's so-called biexciton puzzle in the field for roughly 3 or 5 years. Meanwhile, there's some ultra-fast studies showing the indication of MOC2, the biexciton binding energy is roughly around 20 milli eV. So what's going on? Well, if you make clean sample, if you do power dependence again, you will see that not only have an emergent peak here, there's also another emergent peak here. So there's actually 2 peaks showing this I-squared quadratic dependence, which is signature of biexciton. Which you can see is actually better than the previous one. It's actually close to 2. What does that mean? Well, now you have gate control. You can control doping in the system, so you can study how the doping affects this 2 emergent peak. Instantly, you can see that this peak happened around the gate voltage close to 0. So this one is actually charge neutral region. This emergent peak, which has a binding energy of 50 milli eV, happens only at a slightly n-doped region. So what happened is that this one is a truly biexciton, which is exciton bound to another exciton, which is intrinsic quasi-particle. But this n-doped region is corresponding to biexciton, exciton bound together and then bound to another additional electrons. So it's actually 5-particle complex. This one and this one. So this one is intrinsic biexciton. This one is actually charged biexciton. Biexciton bound to an additional free electron. And we have B field to show that. We can also do so-called valley polarization measurement. In this case, as we said, we can use circular polarized light to excite some material. So let's say we use right circular polarized light to excite a material and detect the circular polarization of the PL. You can detect the same polarization in opposite direction. So for exciton, you can see right away that this one shows the circular polarization, right, which is a result of valley polarization. This XX minus peak actually has fairly large valley polarization as well. As a result, the configuration of the 5 particle can be instantly shown as here. So you have 1 electron here, 1 hole here, 1 electron here, and this one can only be here because otherwise it's going to have negative valley polarization. So we have a valley polarized biexciton. How about this biexciton? This is a little bit complicated, so I might skip the analysis here. But by analyzing the PL intensity in the B field, you can see the biexciton is configuration is as such. So you have 1 electron here, 1 hole here, 1 electron here, 1 here. One thing I want to emphasize is that if you look at the chart biexciton or biexciton by nature, the reason you have a fairly small threshold for biexciton in this case is that if you look at this 4 quantum particle, it's 1 electron hole pair here, but another electron hole pair here. And as we will discuss later, this electron hole pair or this electron hole pair, both are dark exciton. As a result, they have a longer lifetime, they have very large density compared to exciton. As a result, it's very easy to form this kind of quasi-particle in this system compared to the traditional semiconductors. Well, now we can do all this magnetic field dependence. If you apply large magnetic field and look at the shift of the PL peak, and you on one spec. So here we can also study the helicity resolve PL. So this one resolve PL from one valley, this one from other valley. You can see that most of peak have, first of all of them are, most of them are linear shift, right? One branch is a red shift, one branch is a red shift. Well, this is just a Zeeman splitting from this E field dependence. So one thing, back to your question about the trion, is that if you look at the G factor, most of them are 4, which is what you expect for exciton. For trion, since the recombination of electron hole is the same as the bright exciton, so G factor should be the same, because if you're using non-interaction picture, the Zeeman shift is essentially the excitation of the exciton will be the Zeeman shift of conduction band minus Zeeman shift of valence band. So in principle, those should be the same. So that's another signature of exciton. Actually, there's one. I'm not sure if you can see it. One additional feature you can see. Well, first, so besides all this linear shift, which consistent with this one additional peak actually cross here, and this one additional peak actually across here. You see that? So this is actually the signature of the dark exciton. So as we mentioned, dark exciton should not emit light, right? Because in plane, for the in-plane dipole, the radiation is strictly forbidden because the spin configuration is a triplet, right? Why do you claim this dark exciton? So people have been looking for this dark exciton very actively. So there's quite two very nice work. One again from Tony Han's group, they apply a very large in-plane magnetic field to brighten the otherwise forbidden dark exciton. Or the Harvard group, they use a plasmonic structure to engineer the local field to brighten this dark exciton. The reason they were able to brighten this dark exciton is that although this transition is strictly forbidden for in-plane dipole, the 2D material is not strictly 2D. It actually has a Z dimension. You have a finite out-plane dipole. This out-plane dipole is not forbidden, it's protected by this 3-fold rotation symmetry and so on and so forth. So this out-plane dipole is not forbidden. It actually has a finite radiation. But why don't you see it? Well, now for in-plane dipole, I'm assuming everyone has done E and M, right? If it's in-plane dipole, the radiation, oscillating dipole in plane, what's the radiation direction? It's out of plane, 90 degrees, right? So you'll be able to see it fairly easily. So most of our setup is normal incidence and normal collection. What if you have other dipole? What's radiation? It's in plane, right? How do you detect an in-plane signal? So that's why the PL is, the oscillation strength is small to start with. So the signal is not huge to start with. In addition, the light is actually coming out from the side, so you cannot see it easily. But this dipole, the maximum is here, but it's quantifying square dependent, so it's not a dramatic change. So if your collection angle is large enough, you're going to collect a finite amount of this light anyway. So what we did is we use a fairly large NA, roughly 0.6, 0.5. That's enough to collect enough signal from the side. So that's why you see it here. But why it's a cross in the magnetic field? Well, what we are trying to do is circle polarization light, right? So we were saying one is from K value, one is from K prime value. So one is the blue shift, one is the left red shift. But now this outer plane dipole radiation do not have this threefold symmetry protection anymore. You actually don't have the same value physics anymore. So the light is actually not circular polarized light. It's actually linear polarized, the P polarized light. As a result, this one can be composed into both left and right circularized component. As a result, from this light, if you apply magnetic field, you actually split in two branches. One is redshift, one is bright-shift. That will be a smoking gun evidence of dark X. So in this case, by making the sample clean, by using relatively large NA, we can directly see the dark X. This sounds reasonable, but we don't have magnetic field. We have to go to magnetic lab for the B field measurements. Right? It would be nice to do it in our own lab. What can we do? It's actually not too bad. As we said, the radiation angle of these two dipoles is completely different. If you have technique to resolve these two angles, you should be able to resolve these. Right? That's what we do. So we build another setup called back focal plane imaging setup. Essentially look at the back focal plane instead of the real device, which is a Fourier transform. In that case, we can resolve the PL as a function of radiation angle. Now you can see for each of the line, that's the resonance peak you see. It's just I'm trying to plot the angular dependence here. If we look at all the excitonic features, for most of them, you can see the resonance is around 0 degree. So for exciton, let's say it's this plot here, right? So maximum is around 0 and it's going down when angle becomes large. But if you look at the exciton, dark exciton, well, we know the spectrum now. So look at this position. The maximum is at the edge, but 0 in the middle, which is what you expected from a radiant dipole outer plane. Right. It's maximum here because that's the cutoff of the angle. We cannot go to 90 degrees. For 0.65, that's the maximum angle we can resolve. What can you use this for? Now imagine we can do this with our own setup. We can control the gate. The question is, can you see dark trion? Right? If you have dark exciton, you dope it with one electron and one hole, you should be able to see dark trions. That's what we see. In the P positive doping side, we see a P trion, dark P trion, and in the N doping side, we see a negative P trion. The signature is the same. If you look at the angular dependence, you will see that. One nice thing of this thing is, probably I don't have time to elaborate here, but dark, as we said, dark exciton is very nice. It's long-lived compared to exciton. But as according to our discussion, this one is linear polarized, does not have value degree freedom. Right? You were able to increase lifetime, but you lost a value degree freedom. Dark trion also has a long lifetime, but it has a finite degree of freedom. So here in this plot, we've identified most of the peaks. This is by exciton, charged by exciton, dark exciton. This is plasma mode. I'm not going to discuss today. There's only 2 more peaks we didn't identify, which is this peak here and this peak here. Both are actually phonon replica of a dark exciton mode, and I'm going to show you why.
What is the temperature?
4K.
4K.
You should be able to see this at around 10K. even 20K, I think. It's quite robust.
Are there any that would show up at room temperature?
Room temperature, no. So a couple of things will happen. So the peak position will shift. The peak will be significantly broadened. A lot of phonon process will come in. So we have a broader peak. So you still see most people claim they see dark excitons, so, but it's going to be embedded in all the exciton peak. How to differentiate them, it's going to be difficult. So let's say these two peaks are we haven't identified yet. What I'm doing. For the first one, that's the so-called XDR, one of them. One thing we found is that for many different devices, whenever you have a dark exciton peak, there's always a peak here at a fixed energy, roughly 20 millieV away from a dark exciton. And interestingly, if you use magnetic field to split this dark exciton, as we said, it's a cross, right? It's a splitting. This also got split. If you do power dependence, this is exactly the same as dark exciton. It looks like this is exactly a copy of this. Then phonon replica would be the first guess. We can also measure the G factor. One thing I forgot to mention is that a dark exciton has fairly large G factor, roughly 10, much larger than exciton. Exciton G factor is roughly 4. If you measure this replica state, it's exactly the same dark exciton. Again, another evidence it's a copy of dark exciton.
Sorry, why it's that large? Can you explain?
Oh, it's fairly easy. Not fairly easy. So if you look at it's essentially the band structure of this. So when for non-interacting picture, what we assume is essentially the Zeeman shift is shift of this minus shift of this. Right? Mm-hmm. And for each of them, you have 3 components. There's normally there's optical component, there's a spin component. Additionally, there's a Valley degree freedom. If you compare to bright and dark, let's say, for example, if I compare dark and bright, this one has same value. So barrier phase is same, but the conduction band is the opposite, right? So that will differ by roughly, say 2 or 4 already. And then you can consider the conduction band. It's just, if you go through the calculation, that's 10 instead of 4. So, and we can do gate dependence again. Let's say dark exciton is, let's say, here. So dark exciton is charge neutral particle, so it only happens in charge neutral region. And this one happens at exactly the same region. It's also a charge neutral particle. Interestingly, this thing actually also polarized. For dark exciton, you can see the value polarization is gone. But for this replica state, it's actually value polarized again. So now it's a phonon replica, but the phonon replica state retain the value polarization information. So how do you do that? So this actually we were helped by Professor Li Yang here. So he was able to help us calculate some of the phonon energy. Actually, one of the phonon energy matches very well with what we've seen, the 21.8 millieV. So what happened is that you actually have these 2 phonon modes. These are 2 linear modes. And the linear combination of these form this so-called chiral phonon mode, where one of the atom is doing this motion, the opposite is doing this motion. As a result, this phonon mode essentially works as an in-plane magnetic field, tilt this spin a little bit. As a result, the originally dark mode is not strictly dark anymore because the spin is not strictly same good numbers it was. As a result, you see a finite light coming out. But the trick is here you have to conserve energy that's conserved through the phonon energy. You have to conserve angular momentum as well. So the pseudo angular momentum of phonon play an important role to help retain the value polarization of this mode. So I'm going to skip the detailed calculation here, but eventually what you see is, as I said before, this dark phonon replica retain the value polarization, right? And we can do the lifetime of that. So that's a dark phonon replica. That's a dark exciton. it's roughly the same lifetime. So lifetime is around 200 picoseconds. It's 2 order of magnitude than hydrogen exciton. So now this gives us exciton, which has relatively longer lifetime and also valid degree freedom. So potentially that would be a promising candidate if you want to use a valid spin. The last one we didn't mention is this one here, we call XI. So it's actually the intervalley exciton replica. The energy-wise, it's very close to the dark N trion and dark P trion. But we know it's a different species because we can do the angular result. The PL show this one actually is coming from in-plane dipole radiation. What happened here is this one corresponding to a particular species of an exciton where you have 1 electron here and 1 hole here. So in terms of spin, this is allowed, but now it has a very large momentum mismatch. So to combine these requires large energy of phonons. Interestingly, this is actually the chiral phonon mode at K predicted by Chen-Liu's graph from Austin a while ago. Xiang Zhang group was able to use pump probe measurement to prove the presence of this phonon mode. Indeed, we actually see the phonon mode through the PL emission. Again, one of the signature is that not only you're seeing it at this energy, which energy matches the K phonon energy, the important thing is that this mode is also valid polarized. That's a result of the pseudo angular momentum conservation. So with that, hopefully I convinced you that we were able to identify most excitonic species in the system. So for these 2 particular phonon mode, they are very interesting in this. And we're still trying to look for the application of those because again, it's very hard to find both long lived quasi particle with a valid degree freedom in the system, but these 2 phonon mode happen to be 2 of them. Again, how to manipulate them, how to create them actively is still under ongoing research.
I have one very naive question. So if they're phonon mode, does that mean like if you increase the temperature, they will actually you will see them enhance?
Yeah. So that's a great question. So I think about this temperature. So first, the phonon mode energy was like 21 millieV. This one is also on the order of 20 millieV. This temperature is 4K. So you can imagine in this temperature, all these phonon modes are frozen. So what you are seeing is actually the emission of phonon. So emitting of phonon and a photon at the same time. How do you engineer this is one thing we were thinking of is if we can create a lot of phonons active using, let's say, mid-infrared or terahertz ionization regime, can we increase the emission of this light? So that's what we were thinking of. If you have the right light source, let me know. So the first one is more easy to do. So it's a gamma phonon mode, so momentum is not an issue. As long as we have the right energy, we should be able to see that. Second one is a little bit tricky because it's a K phonon. How to activate the K phonon? We need to satisfy both momentum conservation and the energy. That's a difficult one. But yes, the gamma phonon will be very, very interesting. We don't have the light source. If you do, let me know.
You need like a terahertz laser for that?
Yeah, so not a strict terahertz is roughly 4 millieV. So this is 20 millieV. So I will be roughly 5 terahertz. So 5 infrared.
Actually, I have another question for a spin forbidden dark exciton. If you were to shine microwave light equal to spin splitting, then could you make them bright?
Yeah, in principle, if you're able, so you're saying, if you're, so if you're saying if you somehow inject energy, flip the spin from here to here, we'll be able to see, yeah, definitely. So this is, I think, very similar to the NV center where you make, so this is spin triplet, right? This is a spin singlet.
So if you were to do this, would you see these dark excitons in the PL signal all of a sudden?
Yeah, so what you might see is enhancement of bright exciton, but dark exciton goes down. So at least bright. So if you look at this, bright exciton is actually not so bright. The reason is very simple. It's an excited state. So it actually has large possibility to go to ground state, right? So instead of emitting light, it has a way to relax energy, go to a dark state. So if you pump it, you're definitely going to see it much, much brighter. Yeah,
I hate to do this to you, but
Sure.
I'm going to ask. The phonon. I'm going to propose a different idea.
Okay.
You have an exciton or
Uh-huh.
multiple excitons in there.
Okay.
They're creating strain on your quantum well. The phonon, as you said, is emission of a phonon, but it's caused because you have a strain in in your lattice, your well. When the electron and hole radiatively recombine, that strain is reduced, and that induces the phonon.
Okay.
That's the mechanism why we get phonon at low temperature assisted. Even
I
though,
see.
so it's cold temperature, they're not populated. But when you have an electron in a hole, it creates a perturbation in your crystal.
Okay.
When it radiatively recombines, it relaxes that crystal and gives off phonon.
I see. I
And
see.
you can see that coherently ripple as the phonons come out. We can
Okay.
see the LO phonon for us, K phonon. You can see that
Sure.
ripple.
Do you have a paper like do
We
you
don't
know?
publish.
Oh,
We're
okay.
waiting for Lee to finish the thing.
We'd love to take a look. Do you know how much strain it's going to induce?
Well, I was going to ask you.
Uh-huh. I have no idea.
So I notice your XO is X0, your exciton is moving around in spectrum to spectrum. Sometimes it's close to 1.73, sometimes it's
Oh yeah. It's a very from spot to spot, sample to sample. We think it's a local strain, but we don't know how much the local
it's that
strain
local
is.
strain. Yeah, so that'll give you an idea on how much you can shift things around, probably 10,
I see.
15 milli EV.
I see.
The other thing is, you have so much cool data here. How in the world can a biexciton have a longer lifetime than an exciton?
That's the thing. Exciton is a bright exciton. The bright exciton, the bright exciton here is not exactly the same as gallium arsenide, like bright exciton bound to one. It's actually one bright exciton coupled to one dark exciton.
Okay, but then when biexciton, one of them has to radiatively recombine.
That's right.
Behind with the other exciton.
Yeah. But imagine you have so much dark exciton around. So probability of this dark exciton bound to a bright exciton is fairly large, right? So if you measure that, if I have to guess, the lifetime will be between dark exciton and a bright exciton. That makes sense.
Maybe. And so if we came in with our ultra-fast lasers and probed your dark exciton, you're claiming I should see that grow in with the decay of the biexciton.
In principle, yes, but the question is, I don't know how to probe the dark exciton directly with a laser. So it's dark because it does not couple to light.
I get that.
Right,
That's
so-
you'd have to probe it some other way.
Yeah. Oh, but once you probe the other way, you have to think about,
Since I totally derailed your talk, I have one other item.
it's fine. So to be honest, I won't have enough time anyway today. So some of the stuff I'll just gone through. But please stop me if you are interested in any of the detail. And also, I'm very happy to answer some questions afterwards. So I think that's pretty much for bright exciton. I think for how much time do I have? 15 minutes. Okay.
You have to go
So this two, I'm going to try to finish in 5 minutes. So essentially, we can turn a magnetic field. We can see Landau level forming, and there's a lot of exciting things we can do. And also, we can do heterostructures. I'll try to do that in 5 minutes. So I told you everything from monolayer, everything up to here. So every peak is not a defect. Every peak is a meaningful quasi-particle. But if you extend the energy even further, we're actually seeing additional peak, at least 4 here, 4 here. This phonon replica of dark trions. And Xiaodong also have very nice paper on this, and we also have paper on this. But one thing we are interested in is turn the magnetic field, turn the Landau quantization, see what's going on. So actually we see something quite cool. If you turn magnetic field, you have Landau level forming in the conduction band, you have a Landau level forming in the valence band. You see the ripple here. There's a ripple from a trion. There's a ripple from dark exciton. It's a very periodic. The spacing here is roughly half of this. What's this peak? Essentially, with this one, you have a very selective Landau level transition, which is done by Chanwei probably 4 years ago, 5 years ago. So we know the transition, how it looks like. If you have Landau levels, you are going to have this transition, which is match these ripples. But if you have I said this is phonon replica, right? If you have phonon process going on, you don't have a same selection anymore. Actually, this selection rule is greatly, the constraint is greatly lifted. So as a result, this electron here can combine with any of the hole here. So you're going to see the energy spacing between this light emission roughly at the Landau level in the valence band. This one, you're going to see the summation of valence band and the conduction band. So that's why it's roughly 1 to 2. But why this is important? So I'm not sure if you are familiar with the 2D electron gas when people trying to study PL as a way to study Landau quantization versus a transport to study Landau quantization, right? These two are different. One is single particle, one is a two particle picture, right? So one of the problem you have is that it's very difficult to compare these two at the same scenario, because in one case you measure one particle, in one case you always measure the combination of electron hole pairs. But here, using the phonon process, I actually lift this constraint, right? So in the trion process, I measure the combination of electron hole pairs. But in the phonon process, I measure the whole, the Landau level in the whole band, the valence band. As a result, I can extract the effective mass of electron and hole simultaneously using optical spectrum. And there's actually something quite interesting going on. First of all, these are not symmetric as what we expect theoretically. And you can see that at this point, they actually diverge, showing a very strong many-body interaction. We don't know why. And we are still trying to do that, but it's actually quite difficult. But that actually brings another question, right? So if you have those Landau levels, so we said in the whole doping side, you are going to see this Landau quantization. How about the intrinsic side? So there's more fundamental questions about, I really should have to finish up. So if you have this Landau levels, right, with a spacing roughly 4 milli eV or on the order of 10 milli eV. Now, in the presence of that Landau level, what's the exciton picture? Your exciton binding engine now, especially in the intrinsic region, is on the order of hundreds of milli eV. It's many of this Landau level spacing. How do you think about this? You cannot think about it as a free electron and a free hole here, right? If you think about this, the energy, quantized energy here is through because you're sequentially feeding the Landau level through doping. Well, if you're sequentially feeding the Landau level, essentially you're blocking this transition because of the electron is fermion, right? Because of Pauli exclusion principle. But I can argue that the exciton is electron hole pair. It's not a fermion, it's boson. Right? Why don't you have a boson condensation instead of sequential feeding of these? So this is actually quite difficult for us to imagine. So one thing we can propose is that to form this exciton, you actually need tens of the Landau levels, electron in these Landau levels. You need tens of holes from these Landau levels. So what you have is not really a simple electron hole pair. You actually have many Landau levels in the valence band and many Landau levels in the conduction band form this quasi-particle. How to understand this, we don't know. But experimentally, what you see is essentially quantization of the exciton energy. And if you plot the energy, it's very much looks like the quantum Hall measurement. Well, you see these plateaus, right? And I just leave it like this. This we published last year, and I try to move on a little bit. We also developed all kinds of techniques. So this one we actually using photocurrent to measure the instead of spectrum. So one thing we can do is we can read out the photocurrent response. This is monolayer WSE2, and using magnetic field, I can record the photocurrent information as a function of spectrum. One thing nice here is that people are trying to study Rydberg exciton in this system, right? If the exciton binding energy is 100 milli eV, if you do an analog comparison with a hydrogen atom, you should be able to see 1s, 2s, all the way to 10s, 20s, right? Like Rydberg atoms. there's a lot of exciting opportunity here because essentially you can using the Rydberg atom concept to do a lot of quantum simulation in this system. But the problem is that the best you can do, the best test you can do is roughly 4s or 5s last year by using a very large magnetic field. It's very, very difficult. But we believe it's not a material, it's the sensitivity of your measurement. So for this particular system, we actually can see all the way to 11s using photocurrent as a probe to probe the Rydberg exciton. We are actually doing a lot of things along this direction. It's difficult measurement, but we believe we actually can push well beyond the 11s. One nice thing of 11s is that the exciton become very, very large. As a result, the exciton interaction is going to be huge. For example, you can even realize the Rydberg exciton blockade the system. With that, you can also make all kinds of heterostructures. The nice thing is for TMD, there's different TMD with different band gap. I engineer the different combination. You can engineer a band structure to do the physics you want. For example, a typical TMD combination gives you so-called type 2 alignment. So valence band in one material, conduction band in another material. So if we have electron whole pair separating 2 layers, they can still form this so-called interlayer exciton. Interlayer exciton has a lot of advantage because lifetime is longer, and so on and so forth. In this case, it's particularly nice because this conduction band are very, very close, roughly 20 milli eV apart. So you can use doping or electrofield to tune the alignment of these two, form hybridization of these 2 layers. So in this one, we sort of demonstrate we can control the exciton in one layer or separate 2 different layers. So we call it anyway. So this was published last year. For different combination, MOSC, WSC2, you can see interlayer exciton also very nicely. But one advantage is that, as we mentioned, for the conduction band, there's a 2 conduction band with opposite spin, right? One is bright, one is dark. But now if you're using heterostructures, this mirror symmetry is broken. So there's no dark state anymore. So both the triplet and singlet are bright again, and it's a fairly bright. That's the 2, if you have a very good sample, that's the 2 peak you have. Again, like what we said, one of the motivation is looking for very polarized particle, which is long-lived, which is the case here. So it's interlayer exciton, it's long-lived, and also vaporization is huge. If you go to this singlet state, the vaporization is actually 100%. But okay, now the most exciting thing for this is Moray system. So you can choose the right combination to form a Moray soup lattice. And this formation of Moray soup lattice give you the flat band in electronic structure, give you correlation. And on top of that, we also have excitons. So what will happen? Moray, I hope I don't have to convince you, it's a very interesting system. So when 2 periodic structures merge together, either with twist angle or with lattice mismatch, you have a new periodic structure with a larger lattice scale. And this one give you reduced kinetic energy. So potentially that's a nice platform to form strong correlation because kinetically it's reduced and also it's 2D. So Coulomb protection is intrinsically very strong. Right? So previously, Feng Wang Berkeley showed that in the twisted WS2 and WS2 layer, instead of twisting it, they tried to intentionally align them either 0 degree or 6 degree. Because the lattice mismatch is roughly 4%, you have Moray soup lattice roughly 8 nanometers. They've already shown that if you form a Moray soup lattice, the exciton of WSC2 is going to split into 3 peaks, and these 3 peaks corresponding to ground state of A site, ground state of B site, and the excited state of B site. So this has been done before. Well, as we said, if you have a system where kinetic energy is reduced, Coulomb interaction is very strong. In principle, you should have very strong correlation. Right? So that's the Hubbard band model. That's the kinetic energy. That's the on-site repulsion energy. McDonald group predict that now in this Moray soup lattice, if you form hole on each of the Moray site, you should form a multi-insulator. So that's the prediction. It's and compared to graphene system, this is much more robust, and we'll show that the transit temperature is more than 1 order of magnitude. because the kinetic and the effective mass is much larger in the TMD system, so the kinetic energy is reduced even further. So it's much easier to form flat band in TMD. So that's what actually people show. So this system is notoriously difficult to do transport measurement. So two groups both did optical measurement. So this is one of the papers. So this is a 3 Maury peak I showed you. If you do a gate dependence, you see that this lowest Maury peak has enhancement here, enhancement here, enhancement here. And they show actually this corresponding to the mod in swing state. So this one is 1 hole per Maury cell. This is 1 electron per Maury cell. Remember, this is generally cell 2. So 1 hole per Maury cell is actually half filling. That's although it's called 1, but it's actually half filling of superlattice. Additionally, one group actually did a very, very clever study. They actually, so transport is very, very difficult, but they find a way to do this capacitance measurement using optical reflection spectrum. So they actually show instead of a peak at n equals peak at n equals 1, there's actually additional feature at 1/3 and 2/3. That's corresponding to 1 electron per 3 Maury cell, or 1 hole per 3 Maury cell, and two holes per 3 Maury cells. So we believe this is a very rich thing for strong correlation, but we cannot do the conductance measurement to see this, right? So what do? So we actually find a collaboration with Trace group at the UC Riverside. So what we do is that we make this structure just like the other groups. Trace group have this microwave impedance microscope, which can locally measure the conductance without worrying too much about the contact resistance. As a result, this is a typical spectrum you see, each dip corresponding to a conductance minimum. You can see nicely that all these dips happen at n equals 1. In addition, we see all this dip at 1/3 and 2/3. But on top of that, we also see this additional feature at the 2/3, at the 1/4, at 1/2, and 3/4. This actually is really exciting. We can also do optical measurement. So this this is a reflection measurement. Reflection measurement, we can only see the n equals -1, +1, but from MRM, we can see additional features. This is really exciting because this 1/3 is a state predicted actually by McDonald as well. That's one of the state candidates for training signal. So we run some simulations through Xiaodi's group at CMU. He's at UW now. It showed that 1/3, and this 1/3, 1/4 phase essentially is this energy minimum for a triangular lattice. But you also have the stripe phase, such as 1/2 and 1/3, which is also a stable phase. That's what we saw. So this was published earlier this year. King-Fai and also Jishan group had a similar result. But in addition, a very specific example, we see this really weird feature at 1/7 and 1/9. This is really exciting for the reason, very simple reason. If you look at the configuration of this requires the lattice interaction much beyond the nearest neighbor. So for this particular case, the electron and electron are 5 lattices apart. Right? Means the interaction is extremely strong. There must be something thing going on, but unfortunately, this is something we cannot reproduce. We can only see it once. We are still trying to reproduce this one. But we believe this is actually true because if you look at the 1/3 is Wigner crystal state, the temperature is very, very high, close to 100K compared to our other result and other people's result. The Wigner crystal should go way around the 20K. So this is a system with a very, very strong interaction. We don't know it's magic. It could be the coupling is very strong. We are still trying to study this. Well, I want to spend one last 2 minutes about this particular data. As I said, this system, we prove that it has a strong correlation. You have all this rich correlated insulating state ongoing. Right? You have multi-insulating states, you have regional crystal state, we also have the stripe phase, right, corresponding to the fractional field. But this system also had a very strong exciton physics. Exciton binding energy is very large. In particular, the WS2 configuration is also a type 2 alignment, meaning you also have interlayer exciton. What will happen to this interlayer exciton at this strongly correlated state? So we take the PL, so this is for 0 degree, 6 degree sample. You can clearly see PL actually shows 1 and -1 state here, 1 and -1 state here, corresponding to reflection measurement. But what's more, if you zoom in for this particular sample, the PL actually already showing 1/3 and 2/3. Here, the PL is much more sensitive than the absorption measurement, simply because this is background-free measurement. In addition, if we increase the power, we actually can see the previous state, which is not there, showing up. For example, for this particular data, we can see that at a higher excitation, you have this n equals 1/3, 2/3, even, okay, I didn't show it here. Even for one of the device, even a quarter also state also shows up. Why the interlayer exciton PL showing such a large change in this correlated state? We don't know. One possibility is that, well, you have insulating states there, so batch constant is changing. So PL is supposed to be sensitive. But we actually think it's probably more than that for this particular example, right? So if we increase, so this is actually published earlier also this year. If we increase the excitation power, for example, here, you can see that the strongest PL is original at this n equals 0 state. But at high power, it looks like the n equals 1 state or -1 state is brighter than n equals 0 state. What happened here? So we have a very naive picture. Essentially, it's not because this one becomes strong, it's because this one does not get as strong as it should, meaning nonlinear process kicks in. So what happened is that at a high excitation power, exciton-exciton annihilation become very important. So all the PL growths become nonlinear, right? But what happened at the correlated state? Well, if you imagine you have a localized electron in the system, once the interlayer exciton coming in, it's going to bond to the localizer state. You form a localizer trion kind of behavior, right? Now, if the interlayer exciton is trapped at the place of localized exciton, the chance for the exciton to meet other exciton is greatly reduced. That means the exciton-exciton annihilation process is going to be reduced. As a result, at the 0, you have fairly large nonlinear process, but here at correlated state, the mobility of the exciton actually was increased, or the nonlinear process was actually forbidden, and then you have relatively stronger PL. But again, we don't have much experimental evidence on this. We are still trying to understand this more, but I'll just leave it like this. So we also do a lot of other materials. We can grow this material. We can use string to tune this material. We are also constantly looking for 2D materials. We also have a little bit of transport measurement going on with this nanoscale device. But our focus now, as you can see, is trying to use this correlated state for quantum simulation or quantum sensing. I think I'm a little bit over time, so I'll stop here. As you can see, there's a lot of work. It cannot be done without other collaborators. And here's all my current students, and also I have 3 alumni playing a very important role in this, for this works. And here are funding sources. That's all for now, and I'll be happy to take questions.
The twisted TMDs. So is transport just difficult because they're so insulating?
Yeah, I think it's mostly contact resistance. Mobility might not be too bad, but the contact resistance is huge.
Yeah.
I mean, to be fair, King-Fai showed some transport data here with simple 2-terminal measurement. As you can see, the overall resistance is just huge. Yeah. But we're also working on that. We've been working on this for quite a while now. It's a very, very difficult problem, but we are making some progress. Essentially choosing the right metal and choosing the right recipe.
You said not every sample shows some of those fractional fillings. Do you know if that's due more to like kind of the non-perfect alignment, or is it just due to disorder, or how much the competition between those?
So let me make it first thing clear. So this quarter, half, all these fractional states are very robust. We've reproduced by quite a few samples. This particular one I cannot reproduce. It's 1719. So like for this one, we know where the n equals 1 state is. We know the density of carrier fairly well, and we know that by that we can actually back up the twist angle. We also do SHG to measure the twist angle. It's not much different. It's within a line within 1 degree. So we see the distribution from like 0.2 to 1 degree. So I don't think it's a particular special in terms of twist angle. I think it's still roughly angle aligned. But again, we don't know what's going on. I mean, if we knew it, we would have produced it. So we were still trying to, but as you can imagine, we actually believe local strain is extremely important. Actually, recently, Feng Wang group at Berkeley showed the STM image of this one. They actually showed the Murray coupling is mostly dominant by the strain at the interface, which is quite surprising. So insurance, we don't know, but we suspect it's not the twist.
Do you know how much strain is induced by the lattice mismatch?
So this I have no idea. I think they mentioned something in the paper. You can check. Yeah,
Thanks.
I'll throw it. I have a different belief on that paper. It comes across as strain, but it's the electron density of the two patterns matching, and you get a variation in electron density, and that causes an effective strain or an effective change in the box that's confinement. So it acts as strain, but it's actually local electron density changing.
But does that require the electron density on both layers?
Was not. Okay. Which leads to all my next questions. Go back to the 1D material.
What 1D material?
Yeah, the 2D.
Oh.
2D, just one layer. Do you have any measurements, whether it's reflection or direct absorption? What is the absorption band gap for your excitons?
I mean, so yes, we do have the reflection measurement. So I actually have this measurement here. So this is a reflection measurement, right? But this is a reflection spectrum. It's a monolayer. You can sort of approximate it as absorption. So exciton absorption is here.
Right.
That's actually 2s. So the absorption is.
So it's shifted from what you're seeing in your PL.
No, it's actually roughly the same. Again, if you check a different spot, it's going to be different from different sample to different sample. But if we believe if you look at exactly the same spot at the same sample, it's roughly the same. Within like 2 millieV.
If you're bored next weekend, go and check that, because I don't think they'll be the same.
Sure.
So I teach Gen Chem.
Okay.
If I bring a carbon atom and I look at a homo-lumo gap, that homo-lumo gap in carbon is very different for carbon and carbon minus. If I bring one more electron into the 2p orbital, screening changes, the energies of the states shift. Same thing happens, absorption, you're accessing empty states. You have your full valence band, you're going to an empty conduction band. Now you have an electron in a hole, your screening changes. Your shielding changes, and that shifts the states.
So that you're talking about the doping dependence of the absorption.
Or photoexcitation of it, either. So what I love about your experiments, you can go in and dope, you can add your gate, You can selectively put electrons in or selectively put holes in, and you're seeing the shifting.
Yeah. So I mean, yes. So photo doping, that part. One thing I'm not sure is how much doping I'm getting in. So one thing we can do, let's say if my absorption light is weak enough. So this one actually light is very, very weak. You can essentially control doping to see how the absorption changing as a function of doping.
Yes.
That's essentially this one here.
Yes.
You do see the shift of the exciton energy, the absorption energy.
That's right.
It's not. You see that, so that's a shift you're seeing here.
That's right. And then that will even further shift from the PL.
Right. But the thing is that this shift is not so significant. The reason is very simple. When you're doping it, you're effectively changing the dielectric constant.
That's right.
You're changing the band gap.
That's right.
And you also change the binding energy.
Sure.
So these two, if I think Steve had this paper claiming that this actually cancels each other.
Not quite.
So
It depends.
yeah. So we actually did I did a very nice experiment which we never published. So how do you screen a material, most dramatically?
Yeah.
Put it on the metal.
Yeah.
We actually did that. The binding, the absorption does not change that much. Within like tens of millieV, like 10 millieV, 20 millieV, but not that much.
So we pick anything with the biggest difference in electronegativities we can. For instance, cadmium telluride, very different electronegativities. So now the lattice becomes very distorted. Even if I just excite one electron up to the conduction band, I get a big shift.
I see.
If your electronegativities are too small, you won't see much of a shift.
Okay.
But
essentially, the excitation of electron hole pair migrated, distort the lattice, and introduce a very high.
Like exciton-phonon strongly coupled local polar material.
almost
Strongly
the polar. Almost the polar.
I see.
And it's for everything we've studied so far.
Okay.
Strong polar.
At varying amounts, anywhere from 5 millieV to 80 millieV.
I see. Yeah, I definitely think about that a little bit. That sounds very interesting.
And then those give rise, what you have is the beauty of being able to shift it by adding one electron, two electron, etc.
Okay.
The other thing at the end there, you're talking about, I'm just throwing it out there, but because of your Morey pattern, because of all that, you definitely have hills and valleys. These excitons can fill those hills and valleys.
Okay.
So you excite, as you're increasing your power, you fill those, then the other excitons don't see those valleys and they become delocalized and can move around. And
Yeah. So that's. We thought of this as well for this one. Yeah.
I think it's spatially image that too at the same time. So add like 5 different dimensions to your plot. That'd be beautiful.
Yeah, I
You
mean,
can make special glasses so everybody can see 5D.
so I mean, we are limited by diffraction limit. So actually, we are actually having some diffusion experiment going on. But like again, the problem is not. So the mobility of this material is not so great. The diffusion analysis is not so large. It's actually very close to the diffraction limit, instead below diffraction limit.
Why though?
I believe it's the mobility. So the diffusion constant is proportional to mobility, and this material is not known to have the greatest mobility.
Sorry, I think maybe you can discuss more because many students are here and they're looking for something to do. But you can keep discussing, and let's thanks for our.
Okay.